This is a ChameleonTuner, automatic ISP color tuning in subjective scenarios. I'm going to focus on one practical ISP problem, tuning a 3D LUT, when the reference images are subjective and not perfectly aligned, like using DSLR photos as targets. The motivation of this work is quite simple, that the geometric misalignment, such as the FOV or viewpoint changes, breaks the correspondences if we compare the pixels directly. However, most of the existing methods in this field are learning-based, which assumes the pixel-aligned pure data. So pixel losses become unreliable in subjective datasets. So what we really need in this scenario is the robust correspondences and controllable optimization instead of black box predictor. Also, in this case, you may think that image registration is tempting, but it can distort the images, so we prefer matching that stays coherent under misalignment. The core idea of the proposed method is the region correspondences plus a controllable 3D LUT search. First, the region level color pairing. We segment both images into superpixels and then use the local feature matching to map the source regions to target regions so that we create a robust color pairs to the FOV and POV changes. And second, we build a data adaptive LUT search space. We find frequent colors, select the anchor vertices around it, and perturb only the local control points so that the LUT edits are efficient, interpretable, and smooth. And finally, we use NSGA and multi-objective optimization to directly optimize multiple perceptual objectives. And this is the end-to-end flow from the misaligned image pairs to the region level correspondences, and then color level correspondences, and then the perceptual losses, and then the NSGA search, then we get the tuned 3D LUT. Here's the key mechanism. For the region level correspondences and loss, we match the key points and then assign them to the superpixel regions to match the region pairs, and then extract the representative colors to form the color pairs and compute color metrics like the delta E, delta H, and delta S. For the 3D LUT search space, we pick the frequent colors as anchors, perturb only nearby LUT vertices, and cluster adjacent control points so that the search stays local and smooth. So instead of learning a global LUT in one shot, we are doing controllable tuning guided by robust color correspondences. Now the results. The primary datasets we focus on is the DPED, which contains the smartphone images as the input and then the DSLR image as the targets. And they have slight FOV and POV differences. And from this table here, you can see that across all categories in the DPD datasets, our methods shows lower delta E, delta H, and LPIPs. The biggest gains appear when the geometric misalignment breaks the pixel-wise methods. That is the other learning-based state-of-the-art methods. And this table also shows that our methods is competitive on aligned datasets, such as the MIT Adobe 5K. And here's the visualization result. You can see from these 4 images how the state-of-the-art learning-based methods fail to construct reliable color correspondences on the datasets with FOV and POV changes, and hence the output image from these methods tends to be more middle grade. And to conclude, our ChameleonTuner is an efficient and interpretable LUTs tuning framework for subjective scenarios. And here are some main takeaways, and also some possible future directions in this work. And also from this color view, you can see how our method is more interpretable. And these cluster points are the source points, their target points, and you can see how our methods keeps the points compact and follows the target hue shifts compared to the baseline methods. Okay, that's all for this presentation. Thanks for watching. And if you're interested in our work, please read our paper, since this is just a short video presentation. And our code will be publicly available on GitHub. Okay, again, thanks for watching.